Three materials, concrete, steel, and asphalt, typically dominate the collective understanding of modern road construction. These components are universally recognized for being heavy, expensive, and characterized by a massive carbon footprint that impacts the environment long after the project concludes. Why would engineers in rural regions of India choose to ignore these traditional industrial standards? It seems simple to rely on proven heavy materials, but in reality, the high cost and environmental toll have forced a radical shift toward a biodegradable alternative. This natural solution is known as coir geotextile fabric. One can notice how this soft, lightweight material is derived entirely from nature before being integrated into the earth. It remains almost unbelievable that a fabric composed of coconut fibers can serve as the primary foundation for heavy trucks and industrial machinery. The process is only gaining momentum as millions of journeys are supported every year by this organic layer. Coconuts growing on trees mark the beginning of this transformation into a technical industrial component. The camera glides along the processing lines, where the raw husks are stripped and treated to ensure durability. At first glance, the fiber appears delicate, but its tensile strength is precisely what allows it to stabilize the soil beneath the pavement. Everything only gets more complicated as the fibers are woven into dense, structured mats. These finished geotextile sheets are transported to construction sites to be laid as a quiet, unseen layer within the roadbed. The equipment gradually rolls the fabric across the prepared ground, creating a reinforced barrier that prevents soil erosion. It is visible how the brown texture of the coir contrasts with the gray earth of the rural landscape. But this is just the beginning of the material's life cycle, as it will eventually break down and merge with the environment. The entire road network in these specific regions now relies on this sustainable foundation to withstand the weight of heavy traffic. Technical processing turns agricultural waste into a high-performance engineering tool that supports the infrastructure. Thus, the journey of the coconut fiber concludes as it takes its place beneath the surface of the earth. 11 to 12 months. That is the exact age a coconut must reach before it is harvested for the production of high-strength industrial fabrics. While most observers focus on the visible asphalt or concrete of a road surface, the actual durability of the infrastructure is determined by a hidden layer deep underground. Why is a material as thin as a few millimeters so critical to the survival of a highway? Without this specialized separation, the heavy structural layers above would eventually sink into the soft earth, leading to surface cracks and total structural collapse. Coir geotextile fabric serves as this invisible foundation, and its composition is entirely biological. It only looks obvious that modern engineering requires synthetic plastics or petroleum-based polymers, but in reality, this material contains no artificial additives. The entire internal structure of the fabric originates from a single organic resource: the fibrous husk of the coconut. In the rigorous field of civil engineering, these geotextiles are never considered secondary components. One can notice how they are positioned precisely between the unstable subsoil and the heavy load-bearing layers of the road. This placement allows the fibers to perform four critical technical functions: stabilizing the soil base, regulating water flow through the ground, distributing mechanical loads evenly, and preventing the onset of erosion. Everything only gets more complicated when considering the specific environmental demands of the Indian subcontinent. It is no coincidence that these bio-based materials have seen such widespread adoption across the region. India possesses a unique combination of geological and climatic factors that make natural fibers more suitable than their synthetic counterparts. The process is only gaining momentum because of the vast rural areas with weak soil foundations and a tropical climate characterized by intense, heavy seasonal rainfall. Engineers face an enormous demand for new road construction while simultaneously working within strictly limited infrastructure budgets. Instead of importing expensive polymer-based alternatives, the industry utilizes the abundant natural resources found within its own borders. 16 billion coconuts are harvested every single year in the southern regions of India alone. The journey of the geotextile fabric begins in these massive plantations, which account for more than 60% of the entire national production. In a year-round hot and humid tropical environment, the coconut is far more than a simple agricultural crop. For the local communities, these trees form a complete and self-sustaining economic ecosystem. The equipment and labor involved support millions of individual livelihoods across diverse sectors, ranging from the food and beverage industry to the manufacturing of heavy construction materials. But this is just the beginning of the material's transformation. Trees on these large-scale plantations typically yield between 50 and 80 fruits per year. To ensure a steady and uninterrupted supply of raw material for the processing facilities, harvesting occurs in continuous cycles lasting between 30 and 45 days. Coconuts are selected when they are mature enough to produce long, robust fibers that are naturally rich in lignin. This organic polymer provides the wood-like stiffness and water resistance required for underground applications. The camera glides along the rows of palms where the most common method of collection still relies on specialized manual labor. 8 to 15 meters is the height skilled workers must climb to reach the fruit at the top of the canopy. One can notice how they ascend the smooth trunks without the use of safety harnesses, cutting down entire bunches of coconuts and allowing them to fall freely to the forest floor. Each individual fruit can weigh between 2.5 and 3.5 kilograms. Because of this weight, the ground area below must be kept entirely clear of personnel to prevent accidents or equipment damage. It seems simple to drop the fruit, but the impact must be managed to preserve the integrity of the inner components. In areas characterized by difficult terrain or where trees reach exceptional heights, laborers utilize long cutting poles measuring between 8 and 10 meters. While this ground-based method increases the safety of the workers, it causes the coconuts to strike the earth with significantly greater force. This increased impact velocity carries a risk of the fruit hitting rocks or exposed roots, which can prematurely crack the husk and degrade the quality of the coconut meat inside. Transition to the next level occurs immediately after the harvest is gathered. The coconuts are concentrated at designated collection points within the plantations or positioned along major transport roads. The equipment gradually moves in as the husks are separated from the inner shells, marking the next technical phase of the production chain. The raw material is now ready to move toward the primary extraction stage without haste. 45% of the total weight of a mature coconut is concentrated in its thick outer husk. Why is this fibrous shell more valuable to the geotextile industry than the water or the flesh inside? It would seem that the fruit is the primary product, but the husk contains a structure of millions of fibers bonded by natural lignin that is uniquely resistant to biological decay. This dense layer typically reaches a thickness of 5 to 7 centimeters, providing the raw material for load-bearing and erosion control applications. Manual labor remains the primary method for extracting this material in many construction-grade processing facilities. One can notice how workers secure the fruit onto sharp metal spikes or pointed stakes to begin the separation. Using specialized knives, they peel away the tough sections from the hard inner shell with rapid, practiced movements. A single skilled laborer can process 500 to 1,000 coconuts per day. At this stage, the material is still rough and moist, but this is just the beginning. Tens of thousands of coconuts are processed daily at large collection centers, where hundreds of workers operate in unison. The camera glides along the piles of husks that initially appear as low-value waste. In reality, this raw material serves as the foundation for roads designed to withstand decades of rain and sun. Everything only gets more complicated as the processing chain moves into its next physical transformation. 60% is the typical moisture level of the coconut husk immediately after it is separated from the fruit. Why is natural drying considered a mandatory stage that is almost impossible to skip? The husks are heavy and saturated, and feeding them directly into fiber extraction machinery would cause the internal structure to tangle and break. This would destroy the tensile strength necessary for industrial construction, leaving the fibers useless for heavy loads. The husks are spread out across vast, open drying yards for a period of 2 to 4 weeks, depending on the weather. One can notice how the material remains exposed to sunlight as the slow drying process gradually reduces the moisture content to exactly 15%. This softens the natural lignin structure of the husk, creating the ideal mechanical conditions for separation. The process is only gaining momentum as the dried husks move toward the heavy machinery. Rotating shafts and rollers tear the husk apart once it is fed into the fiber extraction system. It is visible how the mechanical action frees the long core fibers from the pith and other impurities. At first glance, the extraction seems to produce a finished product, but in reality, the fibers still harbor enough moisture to develop mold during storage. Transition to the next level requires an additional phase of stabilization. 3 to 7 days of further drying are required to bring the moisture content down to a critical threshold below 5%. This specific level makes the fibers lighter and ensures their mechanical properties remain unchanged during long-term storage. The process does not end at this stage, as the dry material must now be converted into a usable industrial form. Equipment gradually moves the loose fibers toward the final mechanical shaping. Spinning machines operate continuously to straighten and twist the loose material into uniform strands. This twisting action ensures a a consistent tensile strength across every meter of the fiber. It is visible how the machines prevent tangling while simultaneously determining the ultimate load-bearing capacity of the final geotextile fabric. The material leaves the spinning stage, transitioning into a calm stage ready for the weaving process. Thus, the coconut fiber reaches the standard required for the further stage of production. 200 to 300 meters of fabric are produced on average every single hour by high-speed industrial looms. Once the core fiber bundles have undergone full drying and reached a state of stable twisting, the material transitions into the final forming stage to be woven into geotextile fabric. In large-scale industrial weaving facilities, the processed fibers are wound onto massive spools and fed into specialized mechanical looms with constant precision. The warp yarns are stretched in parallel across the frame to establish the primary load-bearing framework of the material. Why is the interlacing of the weft yarns performed at such specific regular intervals? The answer lies in the engineering requirements of the mesh. This interlacing creates a characteristic grid structure where the openings typically range from 10 to 25 millimeters in size. This specific dimension is large enough to allow rainwater to pass through the barrier freely, while remaining small enough to maintain the structural stability of the underlying soil. One can notice how the equipment gradually builds the mesh as the shuttles move back and forth at high velocities. 100 kilograms of core fiber can produce approximately 250 to 300 square meters of fabric when manufactured at a standard width of 1 meter. But this is just the beginning. The weaving density directly dictates the speed of the balloon, which operate without interruption to meet production quotas. At first glance, the process seems entirely automated, but in reality, the mechanical tension must be monitored constantly to prevent fiber breakage. Hand weaving of core geotextiles continues to be a vital practice in many rural areas of India, despite the prevalence of industrial plants. Simple mechanical looms are utilized here, and the entire process relies fundamentally on the tactile skill and decades of experience possessed by the weaver. Output is significantly lower in these settings, often reaching only a few dozen meters per day. It gets more complex further on. The weaver must manually set the tension of the warp fibers, control the exact spacing of the mesh, and maintain a steady physical rhythm while passing the weft through the heavy wooden frame. Hand-woven material offers high adaptability to specific terrain conditions and unique use cases that standard factory rolls might not accommodate. After the weaving is completed, every segment of the fabric is inspected for quality and structural integrity. The material is then rolled into large, heavy coils and prepared for logistics transport to various construction sites. The equipment gradually winds the finished product into tight cylinders for easy handling by cranes and loaders. When these rolls of geotextile fabric finally arrive at the construction site, they enter the most critical stage of their functional journey. They are destined to become the quiet, invisible foundational layer that supports the entire weight of the road structure above. Before a single meter of fabric is unrolled, the subgrade of the earth is leveled and thoroughly compacted. This is done to remove uneven spots, sharp stones, or hard objects that could puncture or damage the organic fiber structure. Why is a stable and smooth base considered a prerequisite for the installation? A rough surface would prevent the fabric from performing its intended engineering function. Therefore, the rolls are placed at the starting point and unrolled precisely along the center line of the planned road. It is visible how the fabric lays flat against the soil surface, pressed tightly to ensure there are no folds, air gaps, or loose sections. The process is only gaining momentum as the foundation takes shape. At the joints where two rolls meet, the edges of adjacent sheets are overlapped to form a continuous, unbroken layer across the terrain. This overlapping ensures that mechanical loads and water flow are distributed evenly from the foundation upward without creating weak points. The fabric is then temporarily secured into the ground using steel stakes or pins. One can notice the pins holding the material in position during the subsequent construction steps. Successive layers of gravel, raw soil, and crushed stone are spread directly over the geotextile layer once it is secured. These materials are then compacted using heavy rollers to form a solid, dense base before the final application of asphalt paving. Everything only gets more complicated as the weight of the road increases. Because of this internal reinforcement layer, the finished road gains a significantly higher load-bearing capacity. The presence of the fiber mesh ensures that the pavement develops fewer cracks and maintains a much longer service life. Even under harsh climatic conditions or heavy monsoon rains, the soil remains reinforced and stable. Thus, the steel and stone of the modern infrastructure find their strength in the woven fibers of the earth. The material is ready to move to the next processing phase without haste. 100% of the coconut is utilized as the white flesh inside the shell initiates an entirely separate value chain once fibers have been diverted to road construction. Why is the mechanical processing of this internal pulp so strictly controlled? At first glance, the extraction of oil seems like a simple pressing of raw material. However, without precise grading and washing of the flesh, the resulting oil would lose its biological value and aromatic profile, rendering it unfit for high-end pharmaceutical or cosmetic applications. The process is only gaining momentum as the cleaned white layers move toward the extraction units. Mechanical pressing or cold pressing techniques are deployed to obtain virgin coconut oil from the dried material. The equipment gradually applies pressure to maximize the liquid yield while simultaneously preserving the naturally occurring fatty acids. One can notice how the oil flows in a clear stream, destined for a diverse range of industries, including food production, skincare, and the manufacturing of bio-based lubricants. This represents one of the highest value products within the Indian agricultural sector, providing a substantial foundation for the income of both processing plants and local growers. It gets more complex further on. Even the solid coconut cake remaining after the liquid has been squeezed out is not treated as waste. It is visible how this byproduct is collected and redirected for use as organic fertilizer or nutrient-rich animal feed. This systematic approach effectively closes the material cycle, ensuring that no part of the fruit is discarded. Alongside the production of oil, the water contained within the fruit has emerged as a high-growth value stream. Immediately after the harvest, workers select young coconuts that meet rigid quality standards for size and weight. These fruits are surface cleaned and undergo hygienic treatments that allow them to remain whole rather than being opened for immediate extraction. The natural mineral content and fresh taste are shielded by the shell itself, but this is just the beginning. The entire fruit is chilled or subjected to light pasteurization to extend its shelf life without compromising its internal composition. In modern facilities, automated systems sort these whole coconuts by their dimensions before they are labeled and wrapped for transport. Throughput in these plants reaches tens of thousands of fruits every single day. One can notice the rhythmic movement of export cartons being packed for shipment to the Middle East, Europe, and the United States. Consumers in these international markets prioritize the experience of drinking directly from the natural shell, viewing it as a minimalist beverage with nearly zero industrial intervention. The process does not end at this stage. From the creation of construction materials to the refining of high-grade oils and the distribution of whole fruit beverages, the coconut in India branches into several parallel industrial paths. Each stream serves a distinct global sector, yet every one of them originates from the same foundational agricultural resource. The transformation concludes as the various products leave the facility, ready for the global market. 100% of the fibers now reinforcing modern infrastructure once existed as discarded husks on the fringes of tropical plantations. Why did a simple agricultural byproduct undergo such a radical transformation into a critical component of civil engineering? At first glance, the husks of coconuts seem like mere waste destined for decay, but in reality, the cellular structure of these rough fibers provides a tensile strength and biological resistance that synthetic polymers often fail to match over long durations. Everything only gets more complicated as global industries confront the exhaustion of fossil resources. One can notice how the heavy brown fibers are processed into complex mats known as geotextiles, creating a stable foundation beneath the asphalt of everyday roads. The equipment gradually weaves these natural strands into a tight matrix that prevents soil erosion while allowing for natural filtration. This process is only gaining momentum as the search for sustainable alternatives intensifies. It is visible how the coarse texture of the material allows it to grip the earth with high friction. Because the fiber is naturally rich in lignin, it resists the microscopic organisms that typically break down organic matter in damp soil. Therefore, the material maintains its structural integrity for years, serving as a silent hero in the stabilization of slopes and embankments. The camera glides along the vast rolls of this fabric, which are deployed across construction sites to replace traditional plastic mesh. Transition to the next level of industrial philosophy involves a return to these organic origins. It only looks obvious to use petroleum-based synthetics, but the transition to plant-based materials reduces the overall carbon footprint of massive infrastructure projects. These fibers serve as a physical reminder that the most advanced technical solutions are often hidden within the simple anatomy of common fruit. The transformation from a plantation waste product to a high-performance engineering tool demonstrates a shift in how humanity utilizes the biosphere. The material leaves the processing facility, transitioning into a calm stage where it becomes an invisible part of the landscape. This model of utilizing crop byproducts for heavy industrial applications represents a significant shift in resource management. Thus, the organic fiber reaches the standard required for the next phase of global construction without haste. This marks the conclusion of a journey from the tropical soil to the core of modern transportation networks.